Good afternoon to everybody. I apologize. Yesterday, I was hoping to join you for the gala dinner, but I got stuck in Zurich because the aircraft was broken, and so my flight was delayed like by 4 hours and a half. So I could not socialize with the ROBOVIS community last night. And also, I have a flight to catch in Malaga at 3 p.m. So I have a taxi booked at 12:50. So I have to make it a little bit shorter. And I hate that, but just as like the classes have started in this semester, and I had to be in the class Monday for the first class of the course, Foundations Robotics, so that's why I could not join the conference earlier. Anyway, in the interest of time, let's go. Just one single slide to introduce my team, the Prisma team. We've been active in robotics since 4 decades now, since the time I did my PhD between 1983 and 1986. So it's been a long journey. And we are about 40 people in robotics, about 10 faculty, and about 30 postdocs, PhD students, technical and administrative personnel. We've been quite brave in getting funded at the European Commission level. We got 25 EU-funded projects in the last 18 years, including 2 ERC grants. One advanced grant I'll tell you about in a few minutes, and then my final slide will be about my current grant, which is a synergy grant on medical robotics. Partnership with a number of foreign institutions and companies, patents, awards, and these are the 6 main research areas in which we've been active, and I'll cover most of them today in my keynote. Also, 2 of my folks started spin-off companies like Neobotics and HeRobots, and also I dare to mention that since 10 years we've been active in medical robotics thanks to an interdepartmental center on advanced robotic surgery involving researchers from 2 departments in engineering, 2 departments in medicine, and 1 department in physics. This is the Icarus Center. So the way I've organized my talk is about four sections, and the common thread, as the title of Keynote suggests, is manipulation and control. And I wish to use the conjunction and, manipulation and control, because I'm a control guy, so probably you would expect robot manipulation control of robot manipulation. But actually, the issue of manipulation involves a lot more than the control aspect. So that's why I'll be speaking about manipulation and control. Dynamic manipulation. What is meant by dynamic manipulation? Is the manipulation of objects in a non-prehensile way, without grasping, and at the same time, manipulation of deformable objects. So what happened when we were working on this in this new area, I just wanted to propose a proposal for an advanced grant with the European Research Council, and I was in the lab with my students and my postdocs, and we were about 2 days from the deadline, and we wanted to find some sort of artifact to show the concept of dynamic manipulation. And I'm from Napoli, Italy, and Napoli is the home of pizza. And it was Napoli to inspire me to propose to use as a benchmark all the phases in the preparation of a pizza. So what do you have? You have like a dough, you stretch the dough, and you make it thinner and thinner. Then you toss this flexible, deformable object. Seasoning is the easy part. Seasoning is like a pick and place that we have in manufacturing, right? But baking in the oven, in the original wooden fire oven, also involves some sort of control challenges because it's an under-actuated mechanical system. So I propose we ordered some pizza because we were working late in the lab, and then I had a sort of a vision, inspiration. My students were kind of, just chasing me because, no, it's not serious. We cannot propose, we cannot submit a proposal for a 2.5 million grant for a pizza-making robot. But I say this is a perfect metaphor to show how complex and how dexterous do we want our robotic systems to be. So this is the Rodiman history. Unfortunately, there is no sound, but I mean, just as like I had some nice sound. So basically, this illustrates the concept of dynamic manipulation. We built a platform, a humanoid platform. We had to make some choices because we wanted to control all the degrees of freedom. So we just built our torso, and then we used 2 Powerball arms manufactured by Schunk, together with the 5-finger anthropomorphic hands. And we involved a Michelin pizza chef into the project, so we were acquiring his motion through a sort of X-Sense suite with gyroscopes, accelerometers, inertial measurement units. And then through the Jacobians, we were transforming his kinematics and his biomechanical data onto the system. So this was, you cannot imagine the coverage that we had in the media, which also was a good way to disseminate what, as robotics community, we're doing. European Research Council places a lot of attention on the dissemination. So this was a perfect media expedient to attract attention towards the robotic community and ultimately our lab. So it was clear to us that it was very difficult to develop a general theoretical framework for dynamic manipulation. So concerning the issue of non-prehensive manipulation, what the best we could do, and this video clip show this, is to develop a number of primitives. So we tried to solve one primitive after the other. So for instance, the one upper right shows the issue of controlling the motion of the dog, of the disc of pizza on a peel, with 2 motion, this kind of like swivel motion and tilt motion. And at the end, you want to control 3 degrees of freedom because you have to control the position of the disc on the peel together with the orientation. So that's why I say this under-actuated mechanical system. Then you see some kind of video like visual servoing, some sort of critical stability issue like balancing a slender stick with a ball with the robot using visual servoing. So that's another application of non-prehensive manipulation. Or maybe balancing the ball on a wheel, on a tire, and the ball can fall on all sides. So it's like, and we were exploiting also the redundant degrees of freedom of the platform. And then you see some kind of simulation like a hula hoop, like a robot doing a hula hoop, or maybe just the one lower left, just throwing the formable object and finding a global optimal problem to find what is the best posture for the robot to catch a flying deformable object. We, after the end of the grant, we did some more work, and this concerned non-prehensile object transportation. So suppose that you want to have a sort of robotic waiter to carry some kind of object, and the object might be placed on a tray. And clearly, because of the dynamics, because also, well, you also have some friction, of course. Yeah, typically, what happens is that the object will unavoidably fall. And we carried out, this is a recent transactions robotics paper in which these results are published, and we did a study with human subject with a haptic interface, and basically, the algorithm that we developed is trying to compensate for the dynamic effects, like, for instance, Coriolis centrifugal effects, and exploiting friction to keep the object in balance, even if it's not in the center of the tray. Some more work we've been doing within a European project on logistics for hospitals. This is a robot used with some kind of sample, some kind of probes. And this is an example of non-prehensile pushing manipulation. So this is a compliant robot. It's a KUKA EVA robot that I'm sure most of you know. And of course, we have a physical interaction, and we have to guarantee that the human is interacting with the the tray of the sample probe, and we want to ensure that the whole thing is stable. And this can be done according to the control framework of passivity. Passivity is a passivity theory. Basically, it shows that there is no energy produced, and in the physical interaction, the system stays stable. And we can modulate the amount of velocity. This is a concept of passivity theorem. I don't have time to go into details, but if you go to the website of our team of Prisma Lab, you also find the downloadable PDF papers if you are interested, or you can contact me. So that's the concept of the energy tank. The beauty of robotics has been experienced recently within my team, because basically, what do we do in robotics? We develop some sort of mathematical approaches, to describe the physical system. And this is one example of the transversality of theory of robotic systems. Because what we observed is that the issue of non-prehensile manipulation is conceptually similar to the issue of a biped, of the gait of the biped walking. So we found this sort of analogy, which was really surprising me. This was some sort of brainstorming with the people in my team. And we found a sort of duality between a multi-finger grasp and a multi-legged stance. Because basically, when you try to grasp an object, you have the contact of the fingers, and conceptually, this is the same issue when you have a multi-legged robot like a biped or a quadruped. So we were able to expand our work on dynamic manipulation to the case of legged robotics, in which there is a connection between a manipulation path and a locomotion path. Of course, we had to do some kind of assumptions, because it depends on the contact of the foot with the terrain. And so, to simplify, we started this work with the case of a flat-feet biped robot, and the kind of juggling system that you saw in some of the videos with the primitives are also similar to the way, just like a biped walks. And since we got a quadruped in our lab, this is the animal four-legged robot manufactured by Anybotics. Anybotics is a startup company funded by Marco Hutter at ETH in Zurich. We did some work with disturbance rejection. Basically, we are using the concept of momentum and acceleration-based observers, just in a way that we can control the swing and the stance of the legs and make it robust to disturbances. Say that the animal, the quadruped, walks on some sort of obstacles, some sort of rough terrain. And also, it's not only the issue of navigating a four-legged robot into the environment, but also we can mount a sort of arm, like just like carrying an object. So the work you saw earlier about just carrying an object on the tray can also be done likewise with the four-legged robot. And so we developed a whole body controller for both walking and manipulation. I don't have time to go into details, but basically, this can avoid obstacles, and you can nicely integrate some approaches that are quite well known in control theory. I'm speaking about model predictive control, which is the usual paradigm that is used also to just try to merge some sort of model-based control system with data-driven, like, for instance, the learning approaches of AI. So this was dynamic manipulation. Then the second part is devoted to autonomous manipulation. This is some old work that we did in one of the European projects, the Safari project, in which we extended the concept of impedance control to become a sort of variable impedance control. And this is very much in line with the Industry 5.0 paradigm. what's the difference in transition from 4.0 to the fourth industrial revolution to the fifth industrial revolution? Is to develop a theory that is customizable to the skills of the individual user. So this concept of variable impedance control, there are some performance index, but basically the KUKA lightweight robot can adapt to the inertial characteristics of the human and just complies with the user in such a way to draw a line with a pen, in a sort of cobotics fashion. I've been teaching robotics now for 40 years. Our new textbook is out since last September, Foundations of Robotics, with my former student and now full professor Luigi Villani, and the two colleagues and friends from Sapienza University, Giuseppe Oriolo and Alessandro De Luca. And the reason why I mention this is that I used to say that the theory of robotics, the realm of robotics, is ruled by Jacobians. Jacobian is the fundamental mathematical tool to understand how to model, how to plan, and how to control a robotic system. And this is one case of the concept of Jacobian applied to the multi-finger hands. You know that the development of multi-finger hands is not as well assessed as the development of the theory of mechanical design, planning and modeling, planning and control for robotic arms, because of the complexity of multi-finger hands and the fact that multi-finger hand involves, in theory, like too many motors, too many actuators. So this is one example of scientific contamination with people working in neurosciences, and they developed the concept of postural synergies. So basically, more than 80% of all the possible grasp of an object might be described by the three main synergies of the hand. And thanks God, this corresponds to the singular value decomposition of the grasp matrix and the first three eigenvectors of the singular value decomposition with the principal component analysis correspond to these synergies. So basically, we can map from the joint space to the end effector space, and then to instead of trying to control too many degrees of freedom, like the multi-finger hand, we can control the equivalent degrees of freedom with the suitable Jacobian. And so we've been developing a controller in the synergy subspace that we test experimentally on the five-finger hand. This is the Schunk hand. Now it's no longer available, but this was a nice example to extend the work dating to my old PhD thesis with the click algorithm, the closed-loop inverse kinematics algorithm using the Jacobian transpose. The novelty here is that we embedded force feedback sensing, and so we have some threshold, so we can make sure that we exert the proper amount of force on the object in such a way to allow the hand to do some kind of power grasp or some kind of fine grasps. And also the generation of the input of the reference input can also be carried out according to some optimization of some grasp criterion. Also, we embedded some reinforcement learning technique with the neural network for a robot manipulator, with the same hand to grasp an object that in the object the robot doesn't know. So through a number of repetitive trials and this kind of PI2 learning process, we can learn after a number of trials how to just grasp the object. A final contribution that I'm going to show is in the framework of another European project. This was the REFIELDS project, together with University of Bremen, Università Vanvitelli, and some industrial partners like KUKA, Swisslog, and DM. DM is a major company for supermarket, retail stores. And the issue here was a depalletizing cell. So, just the pallet come with a number of objects, and of course, you cannot pretend that you can scan the barcode, because, that depends whether it's visible or not. So we developed this kind of special gripper with the forklift and the load cell, a force sensor. So merging vision and force feedback, we were able to do this autonomously in a way that the robot recognizes what is the content of the box and just sort out the various boxes to the trays to be delivered to the shelves of a supermarket. So this was autonomous manipulation. The third segment is devoted to aerial manipulation. And this is another story I want to share with you, because research and community building and teamwork is also built through a number of stories. And I got a phone call from a colleague in the University of Bologna, alma mater, Lorenzo Marconi, control guy, and he wanted to get us involved, this was 2009, into a project on aerial manipulation. And we had no background in aeronautical engineering, aerospace engineering, so we didn't know the dynamics of flying robots. And actually the drones, the flying robots, were being used since a long time just as a sort of flying eye. What was the new challenge? To develop the concept of the flying hand, so to do some kind of aerial manipulation. And my team, they were skeptical. I say, come on, we are control engineer. We can derive a mathematical model of the dynamic system, and we can understand what are the control issues, what are the motion planning issues, and what are the sensing issues, and also the contact issue when the aerial robot is in contact with an object. So that proposal was successful, and this was the iRobots project. And then we worked together with other colleagues in the European community. Juha is one of them. I'm glad to see him again. So I'm going to show you some results on aerial manipulation just through a number of European projects in which we were active. This is the idea of manipulating for crawler deployment and retrieval of a big object. So within this project, we were able to mount a lightweight robot by KUKA as a payload to a huge octocopter, so with 8 rotors, to do some sort of deployment and retrieval of big objects. Another work we did is the concept of cooperative assembly. So to use 2 or more drones, multicopters, to do some sort of task. And this was done autonomously. So this is a typical clutter environment with some obstacles. And here we have a fully autonomous assembly system. So there is no planning. You don't need to have a drone pilot to do this. So it's all autonomous. And we have a 6 degree of freedom arm, and also a simple 1 degree of freedom gripper. And so this was some experimental work that we did to do a sort of autonomous assembly of the sticks for a sort of truss structure, in a sort of clutter environment. Then some other work that we've been doing on inspection and maintenance, both of industrial plants and civil infrastructure, concern the issue of non-destructive testing. So this is the UT inspection of concrete structures. You might remember the tragedy of the Morandi Bridge in Genoa that collapsed 8 years ago, and 43 innocent souls were killed. This was sadly also because of lack of systematic inspection and maintenance. And so we developed this drone. This was designed in the house with a direct force torque control in such a way that the drone can just check the structure, the concrete structure for a viaduct. This is a viaduct of the Tangenziale in Napoli, to check if there is any kind of crack, any kind of failure into the concrete walls. And so for this, we're using a tilting quadcopter with a simple 1 degree of freedom, because we want this to be always orthogonal to the surface. And another application of aerial manipulation is encountered for the inspection and maintenance of high voltage power grids. And here, there was a sort of keen idea to exploit the magnetic field of the line to automatically recharge a drone. Because one of the caveats of using drones is the autonomy. Because the payload has to be traded off against the power of the rotors. Typically, the autonomy is about 20 minutes or half an hour. In this case, we have installed an automatically recharging station. So just the drone flies, just lands on the line, and then this is the recharging. And in this case, we have this project that is just for the bird diverters. Because when the birds migrate, they overload the line, and so the line can be damaged. So just placing these bird diverters on the line, and this is a sort of job that is high risk, and also it's kind of expensive to be done by humans. So it's clear that this can be replaced by using robots. One more example of aerial manipulation for non-destructive testing, in which we have extended the work with a simple degree of freedom contact to the case of a 5 degree of freedom lightweight robot arm. And basically, we're doing some inspection of the surfaces in which not only we care about the position, and also we're using ultrasound sensor and other kind of sensors like eddy current sensors, but basically it's a load cell. So we can modulate the amount of force, and also we can control this force. So it's nice to see that the validity of the approaches that we had developed theoretically for ground-based manipulation to also work in the air while the drone is flying and everything is stable. I mentioned some industrial application. One of these applications is just to check the thickness of the pipes. Think about a big plant like oil duct or gas duct, and we have to check if there is any potential crack along the pipes. And so we developed this 26 degree of freedom hybrid drone that flies, then saves energy just by landing on the pipe, and then just with the little wheels roll along, and then is a tool to check the thickness of the pipe. So, and also in another follow-up project, it's not shown here, we actually developed this in a modular fashion. So the drone flies this kind of robot like a snake, and then, so we call this project Koala, like the animal in Australia, and does all the thickness check. And then the drone flies back to recover the koala and carry out the mission. Also, speaking about a hybrid system, this is the beautiful Gulf of Napoli, sunny. Unfortunately, we have rain today in Marbella, so you saw the island of Capri, and this is a sort of aerial aquatic drone. So we can do this autonomously for deep water analysis, and we tested in the Gulf of Napoli. So this is Capri, and so basically we have a path. This is planned, and the drone goes, and then lands on the water. And once it has landed on the water, there is a sensor probe that can go as deep as 50 meters deep and can do some parameters like temperature, like salinity, like pH of the water, like pollution, and all kind of biological samples that you want to do, inspect any kind of basin. Could be like salt water, could be a lake, could be any kind of so this is landing, and then you see the final part of the task with the probe just going underwater and just checking some kind of biological and polluting parameters. And we are currently extending this work also because the idea, you saw the buoyancy mechanism, for floating, okay? The idea is also we have empowered this drone with thrusters, because not only do we want to land on the water, but also with thrusters, we also want to do some kind of navigation in such a way that it's a really transformable robotic system that you don't have to fly to another spot, so you can navigate, and so just some extension of the work. The final part of my talk is about haptic shear control. What is meant by haptic shear control? It's just the merge of two concepts. One concept is haptic guidance, as in the work of the object transportation I show, and the other concept is shear control. Shear control is trading the level of autonomy when you have a physical human-robot interaction system. So what is the autonomy? You know that there's been a taxonomy of autonomous robotic systems, which was published in Science Robotics 4 years ago, in a sort of survey paper for surgical robotics, the 6th level of autonomy in robotic tasks. So the idea is to reduce the operator's physical and mental workload and to entrust the robotic system to do some part of the whole task autonomously. And I'm going to show you some examples. This is a dual-arm semi-autonomous system in which we have been developing a vision-based control, collision avoidance, and also with the haptic interface. I mean, the system is driving the motion of the operator to the haptic interface in such a way as to avoid the typical constraints of manipulations. What are those constraints about? Path limits. You can also have a sort of virtual wall, if you wish, collision, singularities of the robotic system, and so forth. And also, I mentioned Jacobians. In the new textbook, you will also find an approach that's been widely used in a number of commercial systems. This is the approach of task priority control. Basically, you can have a stack of tasks, and like task 1, task 2, task n, and according to some sort of intelligent expert system, you can shuffle the priorities of the task, and the mathematical game is to project the task with lower priority into the null space of the Jacobian of the task with a higher priority. So this is the concept that we developed, and this was quite successful in the framework also of a passivity-based control, to guarantee that the whole human, physical human-robot interaction with the human in the loop stays stable. We apply this concept to the context of robotic surgery, and we developed the concept of the so-called virtual fixtures. We talked with the surgeons a lot, and we discovered that besides the physical and mental stress of the surgery itself, a big portion of surgery involves the suturing, because suturing is very time-consuming. Suturing comes at the end of the operation, and it must be done in a very accurate way, because if you have removed some organ, if you have removed some cancer mass, what you have to assure in the suturing is the anastomosis, because if some tissue has been removed, you have to match in such a way to recover the anatomy of the organ where you have operated. And this is very time-consuming. So why not to have robotic systems assisting the surgeon? And this is the case of the concept of virtual fixtures. Basically, the surgeon is kind of advised by the algorithm that computes some kind of optimal paths for suturing. And of course, from a deontological viewpoint, the responsibility and the decisions are always being taken by the surgeon. And this is another study that we did on robotic surgery, in which we are comparing different techniques. The classical full teleoperation technique, like in the Da Vinci surgical robotic system, with supervised control, shared control using virtual fixture, and shared control using orientation mapping. And this is the study in which we are testing the various algorithms. The final slide I am devoting for my talk today is our current Synergy grant. This is funded by the European Research Council. This is a joint project with 3 friends and colleagues. Kaspar Althofer is the head of the Advanced Robotics Lab at Queen Mary University of London. He was the general chair of ICRA in 2023 in London. Sébastien Ourslin is a big expert on AI and medical imaging at King's College in London. And then the user of the technology is the surgeon, Alberto Arezzo, is one of the top surgeons for endoscopic surgery. He is the current president of the European Association of Endoscopic Surgeons. What is the challenge here is to fight colorectal cancer, because sadly, colorectal cancer is the 3rd worst killer, and the level of mortality is about 50%, because in 2020, there were 600,000 cases of CRC diagnosed in Europe, and 300,000 people died. But the level of mortality of the cancer per se, of the cancer itself, is not that bad. Why is that? Because people do not undergo systematic screening And the best and only reliable technique is colonoscopy. But with colonoscopy, you only have a diagnosis of the suspect cancer mass. And what you have to do typically is to take a bioptic sample and to analyze, and then come back a month later, a month and a half later, depending on the stage of the polyp. You have to decide whether you can do this with another colonoscopy and some tool, okay, which is quite rudimental, or you have to do some kind of open surgery or laparoscopic surgery, usually accompanied by radiation and chemo treatment, okay? So our idea, our revolutionary idea with this Synergy Grant project is to develop a sort of theranostic procedure. What is theranostics about? Theranostics is to do the therapy while you're doing the diagnosis. So we want to be able to stage the polyp in situ and also in the final year of the project in 2030 in vivo. We will test with human volunteers. So we have a multi-sensing technique to detect the stage of the polyp, and then with a micro-manipulator, I'm going to show a video in a minute, we will do the actual surgical operation. And in a way to guarantee safe oncological margins. Because the technique that is used with this kind of hook to smear the polyp guarantees only 50% of the cases. And there's a 50% risk that the cells are spread and there is a risk of metastasis, which is very bad for the human. So this is a kind of rendering illustrating the concept. So this is the patient ready on the table for a colonoscopy. And instead of using this rubber colonoscope, what we use is the concept developed by Kaspar and others, is the eversion robot. So it's a tip-growing robot. We pump air, so it's pneumatically actuated, and this eversion robot creates a sort of tunnel, shuttle in the colon. You can do some rinsing of the residual feces after the purge, after the preparation, and then you're ready to do the inspection with the capsule. The capsule already exists. It's been patented by Alberto and other researchers at Scuola Sant'Anna in Pisa, in the group of Paolo Dario. And this capsule just navigates and stops in proximity of the suspected polyp mass. Then you have to do the sensing, and you have to do the staging of the polyp. But then how do you operate then? And this was our idea, to use a negative gradient of the pressure in such a way as to suck the polyp inside the operating theater. So this is the capsule with white light illumination. That's the rinsing channel there. And this is the multi-sensor probe that we are developing that embeds all optical ultrasound as well as photoacoustic endomicroscopy. Because the more subtle issue is the removal of flat adenomas. Those are almost impossible to try to excise with the current technique. And once you have staged the polyp, you have this bimanual micro-robot with a cutter and also with a fenestrated grasper in such ways to cut around the polyp mass and remove the suspect mass in one shot. So you do the diagnosis and you do the manipulation in one shot. And the project will be over by 2030, and the ambition is also to do the clinical translation into a technology with a startup company and probably sell this technology to, this is our mission, to one of the big players like Medtronic or just like Stryker, all the players that develop medical robotics technology. So that's all I have today. My inspiring motto, as most of you know, is keep the gradient. Thank you.